Chemistry for Physical Science, 6th of September, 2018, and it's the study of matter. Okay, so you guys have done a very good job of defining observations. Now, obviously measurements are quantitative data that we're taking about matter. What measurement did you make in Lab A? One. You only made one as far as I can think. What quantitative measurement did you make in that lab? So a quantitative measurement is one that involves numerical information. Quantitative, quantity. What quantitative measurement did you make? Talk to one another. So I was thinking of when you massed the sodium chloride. Massing sodium chloride is taking a quantitative measurement of the mass of the sodium chloride. But that's right, you also measured, well, and the lab doesn't do a good job of having you calculate the volume of liquid dispensed, but you did take measurements on the volume of liquid that was in the burette, and you were supposed to take for initial and final reading. Those are all direct information that you get. Now, we also make inferences in chemistry to understand matter, and a lot of this is when we're talking about things at the actual atomic or molecular level, the tiny little view. Because there are a lot of things. Okay, so direct observations are pretty obvious. Those inferences really are what we have to think about when we're thinking about the subatomic, or not the subatomic, but the atomic or molecular level. When we're thinking about things that there's no possible way we can observe. We can infer from the behavior of matter what's happening at that atomic or molecular level. But we have no way to directly measure. Do you understand that we cannot see an atom? Do you all understand that? Every now and then I have somebody who pops in and says, but with a microscope? No. Not with a microscope. Recently there have been some developments where we've seen sort of fuzzy images that represent atoms, but we can't see them. So as we start to get into atomic structure stuff, we're going to be talking about how the... Okay, so where were we? We know things about the atom. We have a model of the atomic structure that we couldn't possibly have observed or measured directly. So how do we get that? We infer it from the information that we could measure directly. So, branches of chemistry, boy, there sure are a lot of them. There's a lot of overlap, and specifically there's a lot of overlap between a few of them. The two that will, well, this whole year, this class, this is all inorganic chemistry. That's what this is. We're going to be doing basic, functional, inorganic chemistry. We'll talk about carbon, but we're largely talking about non-carbon containing compounds. We're talking about ionic compounds. We're talking about acids and bases and salts. And this is a good foundational chemistry. If you go on to a program where you're going to have to do a minor in chem or a year in chem, general chemistry at the college level is inorganic chemistry. If you're going on to anything with the biological sciences, the pharmaceutical sciences, you're going to add to that, the second year of study is usually organic. And organic is where we get into the big carbon compounds. You're made of a lot of carbon compounds. Oils, petroleums, pharmaceutical chemicals, methane, propane, butane. These are all organic chemicals. Be careful. Chemists like to laugh at people who enjoy eating organic produce or organic farmers, and I always get irritated with both of them, because here's what chemists do. You don't really need organic. Oh, quit being a jerk. You know what they mean. Organic chemicals are not the same thing as organic vegetables. And as a matter of fact, they're pretty much polar opposites. So we're talking about like organic agriculture. We're talking about not using organic chemicals, because all of the big heavy-duty insecticides and herbicides and pesticides, those are mostly organic chemicals. They're covered in the branch of chemistry that we call organic chemistry, because they are large carbon-containing compounds. So when you hear somebody snicker about something like that, you'll know that, just stop it. You know what they're talking about. Those carbon-containing compounds are pretty important to us because we're carbon-based life forms. A lot of the chemicals that work in our body are carbon-containing chemicals. Those pharmaceuticals are carbon-containing chemicals. If you are going into pharmacy science, you're going to do a whole bunch of organic chemistry, and you're going to follow that up with one that's very closely related to it, which is biochem. Biochemistry is specifically looking at substances and chemical processes in living things, in you, in a dog, in a bacteria, in an earthworm, in a tree. Heavily dependent on organic chemistry, but also brings some sort of new things to the table. There are a few compounds that would be studied more in biochemistry than in organic. Then we get into the three that we don't really touch on here: physical, analytical, and theoretical. So physical actually ends up having a lot to do with heat energy changes in chemical reactions. We don't get to that in a Chem 1 course. If we manage to pull an AP Chem course off next year, there's a lot of physical chemistry in there because there's a lot of heat energy change stuff in there, what's called kinetics in chemistry, and that's all physical chemistry. At the college level, physical chemistry is pretty mind-blowing. At the AP level, I won't say it's easy. So it's a challenging area of study. But if you want to understand the heat changes that a reaction goes through, if you want to understand within a system how a chemical reaction is going to give off energy and how much energy the system's going to have to absorb, you need a knowledge of physical chemistry. Analytical chemistry really, in a way, can relate to any of these. Because analytical chemists take unknowns and they make them into knowns. So they have to understand inorganic and organic compounds, and they have to understand all the techniques that you would use to identify a compound. The one question in the reading about the rovers on Mars, they actually carry an entire analytical chem lab in their belly, which is so cool. And I think a few people had said, well, wouldn't that be inorganic chemistry? Well, they are looking at a lot of minerals and salts and things like that, but what else are we looking for on Mars? What are we looking for? We're looking for evidence of life. I mean, we're past the point where we think that we're going to find any little green men popping up into the viewfinder, but if we find organic chemicals that are similar to RNA or DNA or other chemicals that we know exist in living things on this planet, then we start to scratch our heads and go, well, what was here? So, yeah, an analytical chemist is going to have a knowledge of both organic, inorganic, biochem, but really they have to have a knowledge of how to identify compounds. Theoretical chemistry, oof, that's big, heavy stuff. That's computer modeling behavior. Nothing we touch on in here, and unless you're going on to a chem major or a chem master's, you're probably not going to do any theoretical chemistry. Okay, we're going to stop there. I will go ahead and post the quiz. You can take the quiz, and then I am going to give you some time to ask any more questions you've got on the packet. And I would suggest quizzing one another on equipment. And you can work with your lab group if you want, because remember, those are the people upon whose shoulders you will be riding for that grade.